Hello everybody, we're going to talk about 6.1 verifying trigonometric identities. And the very first thing you need to do is to recall the basic identities from section 5.4. Those were our reciprocal identities, our ratio identities, and the Pythagorean identities. These are the basic ones that you are expected to know when it comes to dealing with all of these identities that we have. Now, there are a few others. For example, we might talk about adding in these even or odd function identities. An even or an odd function includes that idea that, for example, if I told you that we had the sign of x and the sign of negative x, they're related because they are odd functions. And we could also think of things like the cosine of negative x being equal to the cosine of x because it is an even function, and so on down the list. These two might be helpful in some different locations. For our purposes, however, for this discussion, we're going to focus on using these identities to help us do what's called verifying trigonometric identities. So we need another definition right here. The definition we need is what is an identity equation in the first place. Recalling from algebra the different types of equations that we had the basic equation, which was an equation where we had one solution, one value of x made it true. There were also contradictions, which were equations that had no true solution. But in algebra, we might have stated that an equation like this one below is an identity equation. And it's an identity because it's true for every value of x. We could manipulate the left-hand side of this equation to make it look like the right-hand side equation. If you don't see that, on the left-hand side of the equation, by distributing x into the first parentheses, I'd get x squared plus 2x plus 3x plus 1 would be the equivalent of saying x squared plus 5x plus 1 on the right-hand side of the equation, because we know that when we add these two middle terms, sure enough, it is the same statement. So this statement is true for every single value of x that is substituted into the equation. It doesn't matter what value of x we pick, x squared plus 5x plus 1 will always equal itself. So we've just verified an algebra identity just by doing a little bit of algebraic manipulation over here. So the question would be, what are we doing in a trigonometric identity that's different? Well, in trigonometry, we're typically given a statement like this one down here at the bottom that's already true. We assume this is an identity, that this statement will be true for any value of x, and our job is to verify that that statement is true by manipulating one side or the other of the equation to show that they're equivalent. Okay? So there are some specific rules that we have to follow here, and the first rule is this. Number one, you can't add or subtract, multiply, divide, or do any other operation that moves one side or the other. So for example, right here, if I have sine of x times cosine of x times tangent of x equals sine squared x, I cannot divide both sides by sine x. That could potentially lead to verifying an identity that might not be true. Right? We might not be able to show that. So we can't do something that moves or divides out terms and so factors, subtracts out terms, or anything else like that. We work on one side of the equation or we work on the other. So from now on, whenever you're dealing with these identities, let's think of this as being a barrier, that equal sign. We can't do anything that moves anything that's on this left-hand side to the right-hand side and vice versa. Now, we can use algebra to an algebraic operation such as multiplication, distribution, subtraction, addition of like terms, and so on in order to simplify one side or the other. And we also can use any trigonometric identity to rewrite one side as the other. So our goal is to rewrite one side and make it equivalent to exactly what's on the other side. So let's say we're asked to verify sine of x times cosine of x times tangent of x is equal to sine squared x. Now, this is sort of an interesting little game. I mean, we can think of it this way. If we are verifying an identity like this, we might actually play the game of one thing in this expression does not look like the other. One of these things just isn't the same. What is it? Sine of x times cosine of x, tangent of x, sine. Tangent of x seems like a sort of an odd thing to be having in this statement. So what would happen if we rewrote it? We could use an identity right here and tell you that, well, on the left-hand side, if I took sine of x, the first term, times cosine of x, the second factor, and multiplied by, use our reciprocal identity. So this is the same thing as saying our quotient identity, not even quotient, ratio identity. Sine of x over cosine of x is the equivalent statement to tangent of x. And what might have tipped me off is that, well, everything else was in terms of sine or cosine, so why not this? Well, doing so immediately makes me see that, look, I've got a fraction right here that has a cosine of x in the numerator denominator of these fractions, and by algebraic expressions we can cancel common factors in the numerator denominator and rewrite this expression so that on the left I get the sine of x times the sine of x, and we're just going to verify that that's the same thing as the square of the sine of x. Well, of course it is. By algebraic expressions, by definition, any quantity times itself is the square of itself. So this is the square of the sine of x. And of course the square of the sine of x is equal to itself. And so we're done. Our identity has been verified. That's exactly what we were aiming to do. Okay. Now, they're not all this easy, but this is an example of what we mean by verifying an identity. You'll notice that I didn't do anything to multiply, add, subtract, or divide from one side to the other. I just simply manipulated the left-hand side of this equation until I had an expression that was precisely equal to the expression on the right-hand side. All right, more to come.